Okay, folks, let's take a look at 4.1 solving systems by graphing. And at the end of today's lesson, what we want to be able to do is use graphs to find the approximate solutions to the system. And the solution to a system is really just the set of values the variable makes all equations true. And what that means in context is that we are looking for the point of intersection. Where do these two lines cross? Where are they equal to the same output? So if you look at some examples of graphs here, we've got a case where we have intersecting lines, so two lines crossing in the plane, and we can see clearly that there is exactly one solution. They could lie on top of each other where the equations are exactly the same. So you see just one line produced, but there is actually two, one on top of the other. They are the same line, and that would have infinitely many solutions because they are covering all the same set of points. And then we have parallel lines. And we've talked before about parallel, and we know that parallel lines never intersect. And so there is never a point at which they will cross and hold the same value. So there is no solution when our lines are parallel. So let's take a look at the first example. So I have a system here, two equations, y equals negative 2x minus 4. Let's go ahead and graph that. And we should be able to notice pretty quickly that these are in our slope-intercept form. So mx plus b, again, we have our y-intercept, and then we have our slope. So that makes these pretty easy to graph. I'm going to go ahead and do the first one in red here. So I'm going to plot my y-intercept. That's down at negative 4. 1, 2, 3, 4. And then I use my slope of negative 2. That's a rise over run. So that means I go down 2 and over 1. We always run to the right, down 2 over 1. And once I have 2 points, I have enough to make my line. And it looks something like that. And we'll go plot the second one here. We'll do that one in blue. And again, I have an intercept of positive 6, so I go up on my y-axis. 1, 2, 3, 4, 5, 6. Mark my point. And this slope is 0.5. Well, 0.5 is just 1 over 2. So as a rise, I go 1 and I run 1, 2. So rise 1, run 1, 2. I'm going to go ahead and go back the other way because this is where I'm going to intersect. So instead of rising and running to the right, I'm going to fall and run to the left. And that helps me very clearly see where that point of intersection is going to be. So now that I've graphed the two equations, I can see that my intersection is right there. And so the solution to this system is going to be 1, 2, 3, 4. So that's negative 4. And then up 1, 2, 3, 4. Okay, so really all that we've extended now is we are graphing two equations and then looking for the point of intersection. Where do they cross? Let's take a look at another example. Okay, looking at number 2. We're going to follow that same form. These are in slope-intercept again. Y equals mx plus b. So I'm going to mark my y-intercept down at negative 2. And then my slope of 1/2, that's a rise of 1 over 2. I'll do a couple more this way because I want to be very clear on where that point of intersection is. And we'll do the second one in blue. mx plus b, so I mark negative 7. Slope is 3, so I rise 1, 2, 3, run 1. 1, 2, 3, run 1. And we can see our point of intersection there. And so my solution to this set is, it looks like 1, 2. So 2 units to the right, that's positive 2 on x, 1 unit down. Okay, let's go ahead and look at number 3. So 2x plus 10, I'll go up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, I'm off my graph here. My slope is 2, so that's 2 up, 1 over. So instead of going up and right, I'll just do the reverse, and I'll go down 2 and left. Because it's the same thing. From here, I would go 1, 2, and then over back to my line. So 1, 2, and then left. 1, 2, and then left. Okay, we'll graph the second one here. Plus 1, there's my intercept. Negative 1/4, so that's down 1 over 1, 2, 3, 4. I'm going to do the reverse, so I come back towards my line. So I'll go up 1 and then 1, 2, 3, 4 to the left. And we can see that point of intersection right there. So the solution is negative 1, 2, 3, 4. And then positive 1, 2. Okay. So let's take a look at some examples where there may be more solutions. So infinitely many or no solutions. So let's graph our first one again. So this one, just to kind of bring back around, this is in standard form. AX plus BY equals C. So there's a couple different ways in which I could handle this. I could make it look like slope-intercept form, right? I could solve for y. So we just, let's do that over here. So I'm going to go ahead and subtract those 15x's. So I get 5y equals negative 15x plus 25. And then we're going to go ahead and divide by 5. So we get y equals negative 3x plus 5. So I could do that, or I could graph these as intercepts also, right? I could go ahead and cancel out and then divide by the 15, figure out where that x-intercept is. I could cancel out the 15x, divide by 5, figure out where that intercept is. So when we worked on standard form, that was another method of graphing. But we're going to go ahead and just change it into y equals here, and we'll use that slope-intercept form in order to graph. So now we've gone ahead and corrected it. So now we'll put it on the graph. So I have plus 5, 1, 2, 3, 4, 5. And I have a slope of negative 3. So I'll go down 1, 2, 3 and run 1. 1, 2, 3 and run 1. And we will go ahead and put a line through all these. And we'll graph the second. This one's all ready to go. Now this is reversed, so I'll just go ahead and switch these. So these are just like blocks. I have a negative or a minus 3x and a positive 5. So I'll just put the minus 3x in front and the positive 5 behind it. And now I can see my slope intercept. I have 1, 2, 3, 4, 5. And then a slope of negative 3. 1, 2, 3, run 1. 1, 2, 3, run 1. And we can see that this is the exact same equation as this. They have the same intercept, the same slope. So these two coincide. They're existing one on top of the other. They are the exact same. So these have infinitely many solutions. So any number I put in for x, I'm going to get the same output for y. Okay, let's take a look at number 5. So I'm going to go ahead and rewrite it. I'm going to go ahead and move these minus 2x's, so I just add those to each side. So y equals positive 2x plus 6. So now that's pretty easy to graph. 1, 2, 3, 4, 5, 6. There's my y-intercept. And I have a slope of 2, so that's up 1, 2 over 1. 1, 2 over 1. And we'll graph the second one. I'm going to go ahead and add 4x. And we'll rewrite that one. So I'm going to move the 4x up front. Divide each side by 2. Okay, so I get 2x plus 4. So we'll plot that. 1, 2, 3, 4. And then a slope of 2. 1, 2, run 1. 1, 2, run 1. 1, 2, run 1. And then again, we should have noticed as soon as we rewrote that equation, slope-intercept form, that slope of 2, but now I have different y-intercepts. So while my slopes are the same, they're going to be parallel, but it's not the same function, it's not the same line. So these lines will be parallel, so they have no solution. By definition, parallel lines will never cross, so these will never have a point of intersection. There is no value that you can plug in for x that will make these two equations the same. Okay? So now we've seen a case of infinitely many, where they were exactly the same, and then no solution when they're parallel lines. Let's look at 6. And again, we'll just go ahead and rearrange this. This is in standard form, ax plus by equals c. So we'll go ahead and move it. I'll do that right down below here. So we'll go ahead and subtract those 4x's. Use our inverse properties, the opposites, in order to rearrange. Separate the multiplication here. We just divide by that negative 8. Negative over negative is positive. 4 over 8 is 1 over 2. And then I have 12 over negative 8. That's going to be a negative. 12 over 8 is going to be a 3/2. Okay, so let's go ahead and graph this. So this one's a little bit harder because of those. So we're going to go up to, or down rather, to negative 3/2. So from there I go down 1. And then down another half. And then from here, I go up 1. That's 1 full unit, then over 2. Up 1 over 2. Up 1 over 2. Okay, so we look something about like that. Then we'll go ahead and take our second one. That's good to go. We're going to go ahead and rearrange that so the x is in front. So I have 1/2 x and a positive 7. So now we'll go up to 7 and up 1 over 2, up 1 over 2. So again, as soon as we saw that, we should recognize that those are parallel. They have the same slope, but they have different y-intercepts. So they're not the same line, they are just two parallel lines. So these again are parallel, they have no solution. Okay, give number 7 a try here. So again, we're going to go ahead and rearrange these. So I'm going to subtract that 3x first and bring it over. So I minus 3x from both sides. Then we'll divide everything by 2. So there's 1. We'll go ahead and graph that. So 9/2, that's 4.5. 1, 2, 3, 4.5. And then I have negative 3/2. So from there, I go down negative 3. 1, 2, 3, and then run 2. So 1, 2, 3, 1, 2. And we'll draw our line. Okay, the second one here, I just need to divide everything by 2/3. Okay, so dividing by 2/3 is the same as multiplying by 3/2. So we're going to go ahead and multiply 3/2 by 3, and then 3/2 x. So there's our slope. I'm going to put that in front. So negative 3/2 x. So right away we should see that those slopes are the same. So we know we got something going on here. They're either parallel or they're perhaps coinciding the same line. And then on my intercept, this would just be multiply top to top. So this would be 9/2. 3/2 times 3. 3 times 3 is 9 over 2. So now we can see that these are also the same. So I'll go up and mark my intercept, 9/2. And I have a slope of negative 3/2. And so we have our coinciding lines again. So these have infinitely many. Okay, so parallel lines have no solutions. The same line, same equation has infinitely many solutions. Okay, so looking at the story problem, let's identify some information that's important to us. Monisha and Holly have 14 more days to finish reading the same novel for class. Monisha plans to read 9 pages each day. Holly plans to read 20 each day. Assuming Holly and Monisha both maintain their reading, when will Holly catch up? So let's take a look. We get some additional information down here, it looks like. They tell me Monisha's already on page 96 and Holly's on page 6. So let's go ahead and model these. So let's start with, I guess, Monisha. So let's see, she's got 96 pages. That's her initial value, her starting point. So those are normally, let's use slope-intercept form. Starting point, initial value, that's a y-intercept. So we're going to go ahead and put that in. And then she reads 9 pages each day. So that each, per, every, those things give me a constant rate of change. That constant rate of change represents the slope. So that's 9 for every day, each day. Okay, so she's going to have read 9 pages each day plus the 96 pages she's already read. And then Holly, she can be modeled. Let's see, she's starting at page 6, so there's her initial value, her intercept, and then she's reading 20 pages each day, so there's her rate. Okay, so then really we want to see, Monisha's clearly ahead here, already at page 96, but when do the two of them intersect? When do they catch? So essentially we just want to set these two equal to each other, or we could graph them. Okay, but really all we need to do, sorry, lost those here. There we go. All we need to do is set them equal. So we'll say, when does 20 x plus 6 equal 9x plus 96? And we'll go ahead and subtract our x's, bring them together. So that's going to leave me with, looks like 11x. Going to go ahead and subtract those 6's. I get 11x. That's going to be equal to 90. And we'll divide by 11. So this happens at the x value of 90/11ths. 90/11ths, let's check that. It's approximately 8.18. Okay, so mathematically this is when it's going to occur. So at some point there, after 8 days, so when she's reading on the 9th day, she will have surpassed Monisha. So she would have need to have read for the full 8, and then in the 9th day of reading, she will have passed. Okay, so that's the point of intersection. That's when Holly's going to catch Monisha. And then how long does it take for them to actually reach? Well, since we know that Holly's going to be the first one done because she's going to overtake Monisha after the 8th day, we can go ahead and evaluate hers. So we'll take her equation. So y equals 20x plus 6. So these are the pages read each day. And then we see here that there are 220 pages total in that book. So we'll go ahead and set the y value to 220. So what value of x do I need to input? How many days before I reach the 220 pages in the book? So then we can go ahead and just solve this. So minus 6. That's going to be 214 equals 20. Divide by 20. And we'll pull up the calculator again here. And so we have 214 divided by 20. So that's going to be 10.7 days. So somewhere in the 11th day that she's been reading the book, she will complete that and have all of the 220 pages read. Okay, let's look down below here a little bit. So suppose Monisha reads 10 pages each day instead. How will that change the length of time it takes for Holly to catch up with Monisha? So all we're going to do there is just alter that equation slightly. So Holly's still reading 20 pages every day starting at page 6. And now Monisha is reading 10 pages starting at 96. So let's see how that alters things. So again, I'm going to go ahead and subtract those 10 x's. Isolate my variable to one side. Subtract these 6. So I get 10x. Divide. So then that's going to be after 9 days of reading. So instead of catching her just after 8 on that 9th day, at the conclusion of it, she will then have caught Monisha. Okay, and then would Holly still finish the novel first? Well, again, as you look at this modeling, you can go ahead and set both these equal. We could test it, but what we're showing is that Holly started behind Monisha, and after 9 days, she's already caught Monisha. So if we were looking at something, Monisha's line would do something like, again, looking at the slopes, she'd have a slope of 9, and Monisha's would have a steeper slope but start lower, and she would have surpassed her somewhere around, say, 9 days. And so then she is ahead of her from that point forward. Okay, if you're going at a constant rate and you catch somebody and you continue at those rates, you will be ahead of them the remainder of the time. So Holly's still certainly going to finish first, and you could simply set both of those equal to 220 to mathematically verify that. Okay, let's take a look at this one. Denise is conducting a science experiment. The blue line represents the temperature over time. For one chemical after being placed in the freezer, the red line represents the change in temperature over time of a second chemical that's been removed. After how many minutes will the temperature of the two chemicals be close to the same? So on this one, we're given the equations of the line. We can see that point of intersection. So that's when this one that is cooling and this one that is warming up out of the freezer come together and intersect. And we see that somewhere probably around 13, -9. Okay, so we can approximate that from the graph. And that really helps us because then when I set these, again, I have a one equation, 0.5x minus 15, and I have a second, -2.6x plus 25. And I just want to know really when do these two equal each other. So we set them equal. And then if I get something that doesn't seem to make sense, approximately 13, -9, I know I've calculated something wrong because I can see from the graph that that's about where I should be. So we'll go ahead and consolidate our x's. I'm going to bring these guys over here this time and make them positive. So 2.6 plus 5, that's going to be 3.1x. In that same step, I'm going to go ahead and bring these 15 over here. So 15 and 25, that's going to be 30, 40. And then we're just dividing by 3.1. So x equals, and we'll bring the calculator out for that one again. So I have 40 divided by 3.1. So about 12.9. Okay, and then what's our units here? It looks like this is in minutes, about 12.9 minutes. Okay, if you've got a graphing calculator, go ahead and watch this part. If not, we're done. I'm just going to go over how to do these in the graphing calculator so that those of you with them know. A couple pretty cool things. Otherwise, bring your questions and we'll get some practice tomorrow. So on the graphing calculator, if we look at these, so I have my two equations here. If you're not real familiar with it, we're going to go to y equals right here on the calculator. That pulls up my list of all of these inputs, y sub 1, y sub 2, y sub 3. I'm going to go ahead and enter these in. So I have 2x minus 3. Now my variable key is right here. It says x, so 2x and then minus 3. And I'll just right arrow down, or down arrow rather. And then I have my second, negative 5x, my key's right there again, plus 6. And I can hit my graph key right here, and I will see these two plotted out in my graph. Okay, and we can pull up, let's see if I can get the little larger image here for you. Okay, so it looks like that. So it looks like it's somewhere right between. If you're, again, unfamiliar, you can go to your window key here, and I can see what those window dimensions are. The standard's negative 10 to 10, and I can see it's scaled by that, going by ones from negative 10 to 10 on the x, negative 10 to 10 on the y. So each one of these then is representing 1. So this is somewhere between 1 and 2. It looks like it's down, not quite to negative 1, so somewhere down there. Now your calculator will actually find that for you. So we hit second. Over here, the trace key, you see that blue calc right up above. So second, that blue key gets me that blue option. And I'm going to go to number 5 here, the intersection. And it asks me to kind of identify based off the first curve where that is. So I'm on the blue line. So anywhere through it, you can really just hit enter, enter, enter. The red line, and it asks me to kind of guess. So I move a little closer. The calculator will crunch those numbers. And I can see my intersections right at about 1.28 or 1.29 if we round. And then the second was negative 0.43. So calculators are really helpful too when they're not really nice intersections. Let's do the next one really quick. So I'll go back to my y equals. I'm just going to overwrite these. I'll clear it, and I'll say 5, my variable key x, minus 4. You can hit enter, clear that one out, and I have negative 6. Be careful if you're not familiar with these. I don't put minus 6. You're going to get a syntax error in the calculator because you're asking it to subtract with that key there. So this is a negative. That symbol's down here, negative 6 plus 14. And again, we'll go ahead and graph those and take a look. And I can see, ooh, make sure I did something right. That looks like a horizontal line, which those equations do not. So let's go double check. And there it is. I missed my x. There we go. There's my first line, 5x minus 4. And here comes the second. Negative 6x plus 14. I see it's somewhere right there, somewhere between 1 and 2. Looks like it's up at 1, 2, 3, 4. Just about 4. So again, second, calc right here. Number 5, we want to find the intersection, and I can just hit enter, enter, enter. And there we go. 1.6 and 4.2. Okay? And if you've got any questions on the graphing calculators, if you have one, feel free to ask tomorrow too. Have a great day.